Hi everybody. I wanted to spend some time today starting to talk about cycloalkanes and how their unique structure impacts their functionality as an organic molecule. So this goes along with chapter 4 in our textbook. If you recall, in chapter 3 we talked about alkanes, which are hydrocarbon molecules that are open chain, or where the two ends don't connect to one another. And we spent a lot of time talking about naming those molecules and their physical structure and the way in which their rotation can give us multiple conformations. Cycloalkanes still fit into this concept of a hydrocarbon backbone, and so we could still talk about decorating them with all sorts of other atoms, functional groups like halides, alcohols, esters, carboxylic acid groups, that kind of thing. But importantly, what we're talking about right now are just single bonded rings. We're going to start out there. Of course, rings can contain double or triple bonds if they're large enough, but we'll see why that can become a problem for smaller rings. So as I mentioned, alkanes all have open chain structure, and so shown on the top are the four smallest alkanes. Methane, the single carbon, and ethane are too small to form a ring, but once we get up to a 3-carbon molecule like propane, which we could have shown as a skeletal structure like that, or butane, 1, 2, 3, 4, we can now bend those ends around and connect them to one another and get similar naming. So we just changed the beginning of the name to include cyclo, and so we get cyclopropane or cyclobutane, pentane, hexane, that sort of a thing. All of the names you learned in chapter 3 as far as the numerical prefixes for the number of carbons, those still apply here. So we could have a cyclooctane, for instance, in an 8-carbon ring. So why do we care about rings? I kind of like to contextualize this when we start. Yes, they're another kind of molecule, and yes, it's another part of chemistry we have to discuss, but very importantly, bioactive molecules contain rings, many, many bioactive molecules. And so just by way of some example, we have some insecticides. The natural insecticide chrysanthemic acid present in chrysanthemums has a cyclopropane ring, and the derivatives of that, or the molecules inspired by that, include some really potent synthetic insecticides like cyhalothrin, which is commonly marketed under a brand name Matador. We can sort of see that chrysanthemic acid structure or the kernel of that in the larger molecule. And it's, of course, been modified extensively to make a new and more potent insecticide. Many pain relievers also contain the same sort of a ring structure. And so we end up with a number of different molecules here shown across the top. We have some common pain relievers you may take over the counter: ibuprofen, the active ingredient in Advil and Motrin; naproxen, the active ingredient in Aleve; and acetaminophen, present in Tylenol and lots of combination products. In those cases, we can see 6-membered rings that are unique, having these alternating single and double bonds. Those are aromatic rings, as we've learned in our functional group lesson. We're going to spend quite a bit of time talking about those molecules. Down below, we have several other bioactive molecules. On the left, morphine is a rather complex multiple ring structure. As you can sort of see, we've got 1, 2, 3, 4 rings sort of in a plane, and then this sort of handle over the top indicates another ring that we can talk about going sort of up and over the molecule like that. Morphine is an incredibly complex molecule. There are many, many derivatives of it that are involved in pain relief. On the far right side, we have cocaine, which is, again, a natural product with a complicated ring structure, 1 ring here, 1 ring here, and then this bridge over the top sort of gives us a second way to think about rings in that part of the molecule. The so-called cane anesthetics come from cocaine. So we have cocaine and novocaine and articaine and all sorts of things used in various ways in the clinic. Also, many signaling molecules and structural molecules in the body contain ring structures. Cortisone is shown in the upper right here with this sort of stereotypical steroid motif, this 4-ring planar structure. We can see other ones here as we go across the list. Cholesterol on the bottom left, other sterols would look similar but different to that, having, again, that similar core. And then a couple of pharmaceutical products. A statin in the upper left, this one simvastatin marketed as Zocor and other brand names, and another statin in the bottom right, pravastatin, marketed as Pravachol, and again other brand names. I've included a couple of hormones here as well, although they just have the 1-ring structure and then sort of the long arching arms, if you will, molecular arms that are classic for a prostaglandin. Just to show you a couple of examples of how two very, very similar molecules can have very different effects. Prostaglandin F2 alpha is involved in childbirth contractions, while E1 is involved in vasodilation. So why ring structures? Well, because they're super important. They are another class of molecule, of course. They're involved in lots of syntheses, lots of important organic reactions, but also important in lots of different applications in agriculture and industry and pharmacology. So before we can really get into a study of these molecules, we do have to know how to name them so we can all talk about the same thing. The naming is very similar to regular open chain alkanes in that we're going to find the longest parent chain. We're going to number that in such a way that we get the smallest numbers for our substituents, and then we'll write the name out with our rules that we've learned before. So finding the parent chain. The parent chain is the longest carbon chain that you can find. And so if we look at the simple cyclopentane on the left, we see obviously a 5-membered ring, 1, 2, 3, 4, 5. If we look at the two molecules on the right, what we'd want to do is compare the ring 5 to the carbon chain 1, 2, 3, 4, 5, 6. In this case, since we have a 6-carbon open chain with a 5-carbon ring, we would name this as an open chain molecule that's substituted with the ring. And so the name here would be a hexane, because it's a 6-carbon open chain, and then we would say that we have a cyclopentyl group attached to it, and that is attached at carbon 1. So this molecule would be called 1-cyclopentyl hexane. Okay, it's important to remember there is no space in between two different letters, so that cyclopentyl L would run right into the H of hexane. On the other hand, when we look at the molecule at the bottom, we have our same 5-membered ring, but now we have a 1, 2, 3, 4-membered straight chain molecule. And so this is one where we now have a cyclopentane. The larger molecule, or the larger part of the molecule, is a 5-carbon, so we name it as a cyclopentane. And then we would say we have a butyl group, a 4-carbon group attached to it. So butyl cyclopentane. You will sometimes see the prefix N here, N-butyl cyclopentane. N in this case means normal, or just saying that this 4-carbon is in a straight chain. So butyl cyclopentane or N-butyl cyclopentane. Okay. Numbering is the same as before. We want to number in such a way to give our substituents the smallest numbers. The benefit here is that you can always have a substituent on carbon 1 because you decide where to start. So if we look at this molecule where we have two different methyl groups attached to a cyclohexane ring, it makes sense, and in both cases we would want to start with one or the other of our methanes numbered at carbon 1, so we get a 1 substituent. And what this slide is showing us is that we can choose to number around clockwise or counterclockwise. We can look at both, and what we're looking for is how we get the smallest set of numbers. And so numbering to the right in the pink, we see we have a 1-methyl group and a 3-methyl group. Numbering the other direction, we still have a 1-methyl, but then we go all the way around until we hit the other one at number 5. Since 1,5 is higher, that's not our choice. This molecule would be appropriately called 1,3-dimethylcyclohexane. If we have a tie, so for instance, if these weren't both methyl groups, if one of these were instead a chlorine, for instance, now we would have the opportunity to number this either as shown in the pink or the other way around, like this in the green, where then we would have a 1,3 substituent in both cases. So now how do we deal with that? The answer here is that if the numerical values are the same, we'll go alphabetically as our tiebreaker. So since chloro comes before methyl, we would choose the one in green, and we would say it is a 1-chloro 3-methyl cyclohexane. Sorry for writing over that, you get the point. Remember the rules from before. Anytime that we have a number and a letter touching each other, we include a dash. Anytime we have two numbers touching each other, we include a comma. And anytime we have letters abutting one another, they just blend together. So here's another example showing that. Now I have 3 substituents. So what we want to do when we look at a molecule like this, and obviously the correct answer is shown, also a couple of incorrect answers, but what I want to point out is that this is a 7-membered ring. So we know that we will have a cycloheptane. Heptane is our 7-membered ring. So cycloheptane. We know that we have a methyl group and an ethyl group, 2 carbon, and another methyl group. Now, in that 7-membered ring, we can think about numbering these in any direction, right? We can start with carbon 1 at any of those points and then number around the circle. What we want to do is minimize our overall numbers. So it makes sense that we would want to have these 2 substituents being numbers 1 and 2. If we started with number 1 over on the left side methyl group, we would have a 1 and a 3 would be our smallest set of numbers. So numbering it this way, with the 1 and 2 in those positions, makes sense. We would not want to do this one at the bottom right because of the numbering scheme. Now we have a choice, as I was saying before. Do I number 1, 2, starting with the methyl going up to ethyl on the left? In that case, I would get a 1, a 2, and a 4 as I number around. In the other case, upper right, I would get a 1 and a 2, and then I don't hit my 3rd substituent until I get to number 6. So since that 6 is higher than the 4, we won't do that one. We're going to have 1 and 2 and 4 are our 3 positions. When we're numbering, when we're figuring out which direction to number, we don't care what's attached at those positions. We just care where the attachment is. So now I've got 1, 2, and 4. Now I would look and say, okay, well, my ethyl is on 2, and I have a methyl on both 1 and 4, and so we combine our name as shown at the bottom. Alphabetical order for the substituents, so ethyl comes first, 2-ethyl, 1,4-dimethyl cycloheptane. And anytime we have, just like before, anytime we have more than one substituent of the same type, we'll use a prefix like that, di or tri or whatever it might be. Okay, so we've just said the same thing again. I'll skip past that. There's another couple of examples with halogens included. Remember, numbering doesn't matter as far as what is attached. So either way, these are 1, 2 substituents. When there's a tiebreaker, we'll go with the alphabetically first one getting the lowest number. So 1-bromo, 2-methyl, rather than the other way around. And at the bottom, just to remind you of the common halogen groups you'll see, those get included just like every other kind of substituent. And so we get fluoro, chloro, bromo, and iodo. Now the big deal with rings is that they have more limited rotational freedom, right? We talked in the previous chapter about how alkanes can be twisted around those single bonds, and we can get all sorts of different conformations. In the case of ring structures, this is a little bit limited. So we're talking about connecting the ends together, and I'd encourage you to build these in your model kits. It's really kind of hard to build the 3-carbon molecule, but 4s and 5s you can build relatively easily. But what's important about this is to say that because we have this sort of fixed plane, we have some stereochemistry that comes up. And so stereochemistry is just talking now about relative position of atoms in space. We're going to use the word or the prefix here, cis, to indicate when those groups are on the same side of a ring, versus trans, down here, where the two groups are on opposite sides of that fixed plane ring. Okay, so it's not enough to just name these molecules that are shown as 1,2-dimethyl cyclopropane. We would certainly name this molecule, or this drawing of the molecule, we would name that with just 1,2-dimethyl cyclopropane. But once we get into 3-dimensional views, we can use our wedge and dash indications to show which side of the molecule those substituents are on. Wedges are indicating that the substituent is coming towards us, sort of out of the plane of the page, while a dashed line is indicating it's going away from us. So showing it like on the top would be a cis, whereas showing it on the bottom is the trans. These are our stereoisomers. Notice that if we are drawing just a flat molecule, so something is drawn just like this, for instance, like we saw in some of those previous slides, I can't distinguish which stereoisomer this is talking about. I would assume it's talking about both. And I would recognize that there are different arrangements that I could have for those methyl and chlorine groups relative to one another. If stereochemistry is shown to me, like this for instance, now I have to include the appropriate prefix. If I'm naming the other direction and I'm given a prefix, I have to then include those dashes and wedges in my drawing. Okay, so we can do some naming here. Again, the naming that we want to look at is to say how big is the ring. So it's a 5-membered ring in this case. How do I number my substituents? Well, 1, 2, 3. And I could have gone in the opposite direction. It wouldn't have mattered here, but I do have to number across the top, so I get 1, 3 as my substituent numbers. And so this would be a 1,3-dimethyl cyclo, and then 5-carbon is pentane. But now indicating that stereochemistry, I have one group coming into the page away from me and one group coming out of the page towards me. And so this would indicate that it's the trans isomer. So either trans or T. Similarly on the right side, using the same scheme, I've got a 6-membered ring. I would number it 1, 2, or the other way around, 1 at the bottom, 2 on the top, it doesn't matter. Now in this case, then that gives me the name so far of 1,2-dichloro cyclohexane. I'm going to run out of room over there, hexane. And then my substituents, I've got this one on a dashed line going away, this one also on a dashed line going away. That gives me the cis or C prefix. And so with that in mind, when we think about what those rings look like, whether we're talking about a 3-membered ring or a 4-membered ring or a 5-membered ring or a 6-membered ring, it's kind of a terrible 6-membered ring, sorry about that, up, over, down, a little better. We can still have a little bit of twisting, right? Each of these sigma bonds is still subject to a little twisting, they just can't spin. And the bigger the molecule is, the more of that sort of conformational twisting I can get. What we're going to find out is that cyclopropane molecules have very high energy. They're sort of bent at a very steep angle to get that triangular shape. And when we look more in depth, we'll see, just like we saw with open chain alkanes, that they do have torsional strain from overlapping or eclipsing bonds, as well as steric strain if there are substituents involved. And so we'll get into that all in the next video. For now, I just wanted to introduce cycloalkanes and their naming and their properties a little bit, and we'll come back and talk about conformations at another time.